Dear students, in the previous lecture, we had started our discussion on the measurement of web search quality. The motivation was that what you can't measure, you can't control. So if you can't measure web search quality, you won't be able to control it. Why did I say that? Because what you can't measure, you can't analyze, and what you can't analyze, you can't control. So it is necessary that we are able to measure the web search quality in some way so that we can improve upon our web search results, right? So I had taken a few generic steps, and therein I had already discussed the recall and precision, which are a couple of very important measures. But in that definition, you must have noticed that all of them are dependent on relevance, how relevant a document is to a query. Now, relevance is a subjective notion. So that is why it becomes important that we go for a subjective measure of web search quality. So that is what we are planning to look into now, a subjective measure. I've already emphasized somewhere that we know two terms, objective and subjective, right? What we have in mind is that objective is something which is true, false, fill in the blanks, multiple choice, that is objective, and subjective is essay type, because that is a but that is a very narrow definition. Subjective means that the answer or the response may vary from person to person. It depends on the subject to which that query is posed. Objective is something which should not vary when you are changing the persons the query is posed at. So we are looking at a subjective measure of web search quality. Now let us see what we are doing here. How do we quantify the quality of search results returned? For that, we must compare the rankings returned by the search engine with the true ranking. Somehow, if we are able to get true ranking from somewhere, then whatever be the search engine results, we shall simply compare it with the true ranking, right? And the closer these two rankings are, the better the search engine is performing, and the farther they are, the worse the search engine is performing, right? So we need to have some true ranking. This is search engine ranking, this is true ranking. So how to get this true ranking? Because once we are able to get this true ranking, we should be able to find out the closeness of these two rankings using what is called the Spearman rank order correlation coefficient. I'll come to that. What is this coefficient? This is primarily meant to have or compare two given rankings. Now the big question remains how to get that true ranking. How to get that true ranking. One may be the objective approach, similarity measures to rank the documents returned. Whatever document the search engine and search engine has returned, you simply re-rank them using one of the measures that we have already studied. For example, TF-IDF, vector space model, or hubs and authorities, or page rank, because they're all the techniques that we've already seen. So an objective approach could be that you employ any one of these and try to get the true ranking. But then in that case, the true ranking will be biased in favor of the technique that we have adopted. For example, the search engine runs on PageRank, and the true ranking also we have done on PageRank. So obviously such a search engine will perform better. Likewise, if there is a search engine which performs on the basis of TF-IDF, and we get the true ranking also using TF-IDF, so that will have undue bias. So this objective approach may have to be replaced by something which is truer, which is more true, right? So for that, we are looking for subjective approach. Have the intelligence of a user to rank the returned documents. Because the human intelligence is supposed to be the ultimate intelligence on the face of the earth. So one way could be that you give the the user the search engine ranking and tell him to re-rank these results based on what his perception about these search engine results are, and you take that as the true ranking and compare the two. But obviously this is an unscalable solution. You can have some 100 users, 1000 users, but the queries that are coming to search engines are millions or even billions per second. You can't employ so many human beings to re-rank all those search results. Re-ranking will also take so much time. Okay? So you cannot actually employ human beings to re-rank the results to get the true ranking of the documents that a search engine has returned in result of a query or in response to a query. So we'll have to find out some alternate means to utilize the intelligence of a user to rank the returned documents. That is what we are looking at. For that, what we do is we measure the satisfaction a user gets when presented with the search results. And towards that end, we monitor the response of the user to the search results presented. One could be explicit, get the user fill up a feedback form. This will be too demanding for the user. The user may not care to give the correct response. So both the things. If I present these search engine results before the user and tell him to re-rank those results or give me a feedback about these search engine results, that will be too taxing for the user. And in the second place, why should a user do it? Why should he rank those results for you? Even if you give out some kind of incentive to the user, okay, so if you do it, we will make something free for you, whatever. In that case, the user may give you any careless ranking. Why should he care to give you the true ranking or the ranking that he thinks is true? So these are the problems with the explicit feedback of the user. Another approach could be to have the implicit feedback from the user by virtue of a close look at the user activity and infer therefrom. Look at the performance or the actions of the user on the search results presented before him. For example, you presented these search results before the user. Some very beginning point could be that look at what result he has clicked the first. For example, he didn't click the first one, he clicked the second one first. So that means the user thinks that the second document is more relevant than the first one, right? And suppose after that he clicks the fifth one. So you can infer that the user wanted to rank the fifth document at second place. So this is how you can implicitly infer the ranking from the actions of the users. So this may be a good beginning point. But then should clicking alone be the entire thing? No, because this clicking is based on the snippet which is accompanying the search result. Whenever you launch a search query, the results are returned and there is some snippet. So that snippet may be misleading, because of which the user clicked a particular document or did not click a particular document. So what next can we look into is how much time he spent. Suppose he clicked the second one first, but then he hit the back button very quickly. He didn't look at that document for too long. So that means he was misled by the snippet to click the second document first, but he didn't spend much time on it. Okay. So these kind of actions we can have. So first, the sequence in which the user visits the document. V1, V2, V and so on. If document I is the kth document visited by the user, then we set Vi is equal to K. If a document I is not visited by the user at all, the corresponding value of Vi may be set to -1. That means he did not click it at all. The time Ti that a user spends examining the document, T1, T2, Tn. For a document that is not visited, the corresponding entry in the array T is 0. So these may be two feedback vectors, the sequence of clicking and the time spent. Can we have more such implicit feedback points? Yes. For example, whether or not the user prints the document I. If he prints a particular document, he's investing in stationery, so that must be very important for him. So this may be a Boolean array Pi, where P1 is 1 if it is printed and 0 if it is not printed, and so on. Whether or not the user saves the document I, right? Again, a Boolean. Saved, then 1. If not saved, then 0. Whether or not the user bookmarks the document, again a Boolean. If he bookmarks, that means he finds it interesting. That is why he's bookmarking. Just as if he was saving, that means he found it interesting. That is why he's saving. Whether or not the user emailed the document to somebody, he will take the pain of emailing it to somebody if only he finds it interesting. So again a Boolean. If he emailed it to somebody, 1. If he did not email, then 0. The number of words the user copied and pasted somewhere. So you can look at the copy based buffer, and suppose he copied the entire document, then you can put a 1. And if he copied a portion of it, so you can load that particular fraction. For example, if he copied half of the document, you can put it 0.5. If 1/3, you can put it 0.33, and so on. Okay. So these are the 7 feedback vectors that we can think of. You can have more added to it. I don't deny that. I'm just trying to bring out a framework for finding out the subjective measurement of web search quality. Now, based on those 7 feedback vectors, what could be the importance value of a document? When feedback recovery is complete, we compute the importance weight sigma j for each document j, where sigma j is some weight wv 1 upon 2 to the power vj minus 1. Vj minus 1, suppose this was the first document clicked, so vj will be 1. So 1 minus 1 is 0. So 2 to the power 0 is 1. So this weight will be 1. Also, for time spent, let us have a fraction. We can estimate the time that a user may require to go through a document of a particular size. That may be based on the KBs. A particular document is 1 KB, 10 KB, 20 KB, 1 MB. So based on that, we can gauge the time required to go through a document. Now, how much time did he actually spend? So this may be the TJ max, the time required to go through the document completely, and the time spent that he actually spent at that document. Again, this is multiplied by WT. All these weights are there as handles. If we don't want to keep these weights, we can equate all of them as ones. Okay. Now WPPJ, whether he printed, whether he saved mark, whether he whether he saved, whether he bookmarked, whether he emailed, and again a fraction of that document that he copied and pasted. So this may be an empirical importance weight of a document. TJ max represents the maximum time a user is expected to spend in examining the document J. Similarly, CJ total is the total number of words in the document J, and out of that, how many did he actually copy? Now here, WP. So as I said, these weights all lying between 0 and 1 give the respective weightages we want to give to each of the 7 components of the feedback vector. If you don't want to have different weightages, you can equate all of them to be ones. This is actually provided as an added flexibility. For example, suppose somebody has got a dial-up connection. In that case, he would want to keep WT as 0. He doesn't want to give any importance to the timing because nobody reads a document online if it is a dial-up connection. Suppose somebody doesn't have a printer, so he would want to keep WP as 0. So that way, this is an added flexibility. These weights, WV, these are an added flexibility. If you don't want to keep them, make them 0. If you don't want to keep any of the components, you can make it 0. If you want to keep all of them as equal, you can keep these weights as 1. So this gives you an empirical, a comprehensive empirical formula for finding out the document importance weight. Right? So let me also say that suppose the document which is clicked first, as I said, that will be 2 to the power Vj minus 1. So this will be 1 minus 1, which will be 0. 2 to the power 0 is 1, that will be 1. If it is the second document clicked, so it will be 1 upon 2, which is 0.5. If it is the third document clicked, then it will be 0.25. And that way, the importance weight of a document decays with the postponement that one can afford in clicking a particular document. Makes sense, right? So this is how you can have an empirical formula. So our scheme of things would be that the user queries goes to a search engine. The search engine ranking comes out. Now this goes to two places. It is placed before the user for his or her feedback. And it is also given to Spearman rank order correlation coefficient to find out the closeness of the two rankings. Now, through the user feedback, which contains 7 feedback vectors, VTP, a sequence of clicking, time spent, whether printed, whether saved, whether bookmarked, whether email, whether how much copied or pasted, right? You find out the document importance weight using the empirical formula we have seen in the previous slide, this one, this empirical formula. And then you do a descending sort based on the document importance weight calculation. So now this gives you the user preference ordering, right? Now this user preference ordering can be taken to be a true ranking, which is compared against the original search engine ranking, and I can get the search quality measure. And these two rankings can be compared using the Spearman rank order correlation coefficient. So, yes, this is the Spearman rank order correlation coefficient. This is the Spearman rank order correlation coefficient. For example, I have, just let me give you an example to make it more clear. So sorting the documents on the descending values of sigma j will yield a sequence, say sigma, right? Let row be the sequence in which the documents were initially listed by the search engine. So what do I mean to say? That suppose, okay, let me take the pen again. Suppose this is row and this is sigma, right? This was the sequence that was coming from the search engine ranking row, and this is the sequence given by the user preference ordering, which we are assuming to be a true ranking. So let row be the sequence in which the documents were initially listed by the search engine. Without loss of generality, it could be assumed that row is 1, 2, 3, so on up till n, where n is the total number of documents listed in the result. We compare the sequence sigma and rho and find Spearman rank order correlation coefficient RS, which is a measure of closeness of two rankings. Right? This is RS, which is a measure of closeness of two rankings, rho and sigma. Now, let us take the example, rank order correlation coefficient. This is given as 1 minus 6 into I is equal to 1 to n di square, n into n square minus 1 is equal to 1, where di is the distance between each individual ranking point. I give an example. Suppose two rankings are there. One is 1526473. The other one is 3152476. I have to find out the closeness between these two rankings. How do I get? First of all, I find out the distance between the individual points. So 1 minus 3 is minus 2. 5 minus 1 is 4. 2 minus 5 is minus 3. 6 minus 2 is 4. 4 minus 4 is 0. 0. 7 minus 7 is 0. 3 minus 6 is minus 3. Then I square them. Minus 2 squared 4. 4 squared 16. Minus 3 squared 9. 4 squared 60. 0 is 0. 0 is 0. Minus 3 squared is 9. And I sum them up. When I sum them up, it comes out to be 54. 4 plus 16 is 20, 29, 45, and 9 again will make it 54. So this is 54. This part is 54, right? So I'll now say RS is equal to 1 minus 6 into 54 upon n is 7. 1, 2, 3, 4, 5, 6, 7. So 7 into 7 square minus 1. So this will be 1 minus 324 upon 336. And when you calculate it, it comes out to be 0.0357. So I can say that these two rankings are close through the, sorry, just hold on a minute. Okay. Yeah. So this will be, yeah. So they are closer by this value, 0.0357. Now you can very well see that if they are exactly same, then what will happen? All these points will be 0, 0, 0. So it will be 1 minus 6 into 0 upon whatever. So which will be 1 minus 0, so 1. So RS varies from 1 when the two rankings are exactly identical, because their difference will be 0 all through. And it varies up till minus 1. If one ranking is exactly opposite of the other, regardless of what n is. That is very important and very interesting, regardless of what n is. If these two rankings are exactly opposite of each other, then it will come out to be minus 1. You can see for a few points yourself. For example, you see 1, 2, 3, 4, 5 and 5, 4, 3, 2, 1. Find out the difference, square it, sum it, feed it in the formula, and then look for yourself. It will come out to be minus 1. Likewise, you take 1, 2, 3, 4, 5, 6, 7, 8 and 8, 7, 6, 5, 4, 3, 2, 1, and then again calculate. So regardless of what n is, this formula will work. Right? So this is a beautiful statistical formula which we can employ to find out the closeness between two rankings. Right? And these two rankings, this will vary from 1 and minus 1. Minus 1 when they are exactly opposite, and 1 when they are exactly similar. So again, the same formula. RS is equal to 1 minus 6, and this is in place of DI square, I have written LAI minus LBI, the ranking of AI and ranking of BI squared. We repeat this procedure for a representative set of queries and take the average of RS. The resulting average value of RS is the required quantitative measure of the search quality in a subjective way. Subjective because we carried out a descending sort on the document importance weight, and those document importance weight is calculated using the empirical formula, which is based on the implicit feedback of the user. So for example, we experimented with 15 queries on 7 popular search engines. This was done some time ago. So for example, Alta Vista, DirectHit, Excite, Google, Hotbot, Lycos, Yahoo, these are the search engines. So this is the sequence. These are the document number, fraction of time, printed or not, importance of document. So we just did it using three feedback vectors: sequence of clicking, time, and printing. You must notice that sequence of clicking is something that you cannot uh, do away with. You cannot leave it out. Why? Because the entire story starts with that. It is only when it is sequenced that you can find out the time, you can print, you can save, bookmark, email, copied and paste. So sequence is always very important. Okay. So this was the user sequence, and the sequence represented by, given by the search engine. We found out the Spearman rank order correlation coefficient for different search engines for 15 queries, and these were the results. Right? Summary of results for 15 queries. These were the queries that we have taken: measuring search quality, mining access patterns from web logs, pattern discovery from web transactions, and so on, so on. 15 queries. We averaged for these 16 queries, and this is the, so you see Yahoo was performing better at that point of time. It was performing better. Google was not performing at that point of time. This I'm talking about. This study was made in 2004. Okay. So at 2004, Google was not performing and Yahoo was performing better. Because I remember I have told you at some point of time that Yahoo used to employ human beings to find out the results of a particular query. So obviously that was performing very well at that point of time. So this is how we plotted them. Yahoo only was positive, Google was least negative. Some Solace that was least negative. Now what is happening is that, let me give you some finer points. Let me go back and give you some finer points. Suppose the search engine returned a few results. For example, top 10 results we considered. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But the user clicked only 3 of them. He clicked this one first, this one second, and this one third. He did not click the remaining ones. Now, as I just now emphasized, if he's not clicking, there is no way that we can find out the time spent or the bookmarking, saving, emailing, and so on. So when he's not clicking those documents at all, that means he is not finding all those documents relevant. So how do I find out their document importance weight? And if I don't find out their document importance weight, then in that case, we cannot do a descending sort. And if there's no descending sort, I can't get the complete user preference ordering. I'll get user preference ordering just in a partial way for these 3 documents that the user clicked. But in order to compare both these, I should have a full list. What I'm getting is just a partial list of the documents that the user has clicked, whereas I require a full list. So how to get a full list? There could be 2 ways. One way could be, suppose, let me take an example. 1, 2, 3, 4, 5. This is the search engine ranking, which was presented before the user, and the user on the basis of sigma j for the document that is clicked and descending sort, he could get that 4 document is very important. That is coming on top, and then comes first document, and then he did not click the remaining 3. What do I do? How do I find out the ranking over here so that they could be compared using Spearman rank order correlation coefficient? So one way could be that I give it the reverse ranking. Why reverse ranking? Because according to this user, the documents besides 1 and 4, that means 2, 3, and 5 were not relevant at all. That is why the user did not click them. So in order to penalize the search engine for giving me extra information, I should rank the remaining documents in a reverse sequence. What all are remaining? 5 is remaining. So I keep it here, right? And then 3, and then 2. Now I find out their differences and I calculate. So the remaining documents I am putting in a reverse sequence so as to penalize the search engine for not giving all the results as relevant ones. Okay, so this was the result based on that reverse ranking sequence of untouched documents reversed so as to penalize the search engine for overwhelming you with irrelevant information. Now using this, we see that most of the results are going negative, which is too harsh on the search engines. There could be a case where I did not click simply because my need could have been satisfied using my search need could have been utilized, could have been satisfied with these 2 documents only. 532 may be lesser relevant, but the user did not click because of his search needs were satisfied using documents 1 and 4 itself. So it becomes too harsh to put them in a reverse sequence. What we can do? We can assume that these 3 documents which were not clicked, 532, were tied up for the next spot. And what is the next spot? I take an average of 3, 4, 5. So I will rather make a change here. I'll say that all of them are ranked at 4 only. Right? All of them are ranked at 4 only. And then I find out di. Di 1 minus 4, 2 minus 1, 4 minus 5, 4 minus 3, 4 minus 2. Why am I doing it? What happens if suppose there are two students who have scored suppose 80%. Two students have, and the third one has scored 79%. So what do? I give them first rank, and then I give the third rank. I skip the second rank because they have scored equal marks. Likewise, what I'm assuming is that what all documents the user has not searched, that should be an average of the remaining ranks. So it should be 3 plus 4 plus 5 divided by 3, which in fact will be 4 only. You got the idea, right? So this is average ranking. Okay. So when I use the same 15 queries, reduce penalization, 2 hours to complete the sequence 6 sigma by listing in a reverse order the documents that are not at all touched by the user. To moderate this stuff, we took to an average ranking method. For instance, if the user looks at the documents in such a way that sorting documents based on sigma j gives the sequence as 4 and 2, then for a total of 10 documents, the sequence sigma would be obtained as 4, 2, 1, 3, 5, 6, 7, 8, 9, 10, right? But the original search engine ranking row with which it is to be compared to get RS is taken as 1, 2, and after that the average of all of them. 3 plus 4 plus 5 divided by 7. So that will come out to be 6.5. So 1, 2, 6.5, 6.5, 6.5 against 4, 2 and the remaining documents. Now these remaining documents could be in any sequence, either reverse or any haphazard, because everything will have to be compared against 6.5 only. All of them are 6.5 minus 6.5 minus, so they could be put in any sequence, right? The logic is that the documents 4 and 2 are anyway at the first and second position respectively, but the rest of the documents are jointly at the next position, which in turn happens to be the average of the remaining ranks. That is 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 divided by 8, which is 6.5. It may be noted that this way it becomes immaterial whether we take the remaining documents to complete the sequence sigma in the same order or the reverse order or any order for that matter, because everything has to be compared against 6.5 only. So when I do it, the relative ranking that has improved, all of them have gone positive. Now Yahoo is still the best, Google is second best, no doubt. But performance of the search engine based on 3 components of user feedback vector VTP, sequence of untouched documents, averaged this time rather than reversed. So this average or reverse is done to convert the partial list into a full list. Okay. So we will stop here and then we will see how can we improve upon this approach in the next lecture. Thank you very much.